Hi students, we have looked at how to draw the dot and cross diagram of your ionic compounds and your covalent compound. Now we will be looking at some of the main properties of the ionic compounds and covalent compounds, starting with the ionic compounds first. Okay, so if you recall, ionic compounds exist as giant lattice structure. So ionic compound, the most common one is your sodium chloride, NaCl. Right, sodium chloride is your ionic compound because sodium is a metal, chlorine is a non-metal. So when it forms a chemical bond between the two elements, they become an ionic compound. Okay, so sodium chloride is the most common salt in the kitchen. If you think about it, the salt that you see in the kitchen cannot be made out of one sodium ion plus one chloride ion, and then it becomes the salt that you can see in the kitchen. So it's actually many sodium ions and many chloride ions joining together to form the salt that you see in the kitchen. Okay, so they form this structure called a giant lattice structure, which essentially really means it looks something like this. Okay, we have a sodium ion attracted to the chloride ion, attracted to the sodium ion, attracted to the chloride ion, and then this attraction keeps repeating in a three-dimensional structure, okay, called the giant lattice structure or the giant crystal lattice. Okay, and then there is also strong electrostatic forces of attraction between the cations and the anions. Okay, so in this case, my cation is sodium ion, Na+. My anions is the chloride ions, Cl-. Okay, as long as there's attraction between charged particles, the plus and the minus, right, we call them strong electrostatic force of attraction. Okay, moving forward, I'm going to abbreviate this ESFOA. Okay, so there's strong attraction between the cations and anions. So essentially the blue parts that I'm going to draw in this picture over here, there is strong attraction along the blue lines over here. Okay, and then this whole thing, the attraction actually holds the multiple ions into a three-dimensional structure called the giant lattice structure. Okay, all ionic compounds exist as giant ionic structure or giant lattice structure. Okay, so with this structure, when I apply a force, okay, the layers will slide such that the like charges are next to each other. So when I apply a force this way, the layers slide. So my plus, which is attracting the minus over here, now my plus is repelling the plus. Okay, my minus is on top of the minus and there's a repulsion. The like charges will repel and the giant lattice structure will shatter. So this explanation will explain the properties that your ionic compounds are brittle. Okay. Next property that we are going to look at is hard. So ionic compounds are hard. Okay, why is it that they are hard? Is because a large amount of energy is needed to overcome this strong ESFOA between the cations and anions. Remember, in terms of chemical bonding, we always have to say the attraction force is between exactly what. In this case, ionic bond is between the cations and anions. We have to be specific about it. Okay, since the electrostatic force is strong, I need a lot of energy. I need more energy to break or to overcome these forces of attraction. So a large amount of energy is needed to overcome the strong electrostatic force of attraction between the cations and anions. Okay. The next property that we are going to look at is the melting point and boiling point. Okay, so ionic compounds have high melting point and high boiling point, and then these will correlate to them being solid at room temperature. If they have low melting point, low boiling point, for example, water, the boiling point is 100 and that is considered quite low. So 100 degrees is considered low boiling point. They are liquid at room temperature pressure. Okay, most of the time, if they have low melting point, low boiling point, they will be gas or liquid at room temperature and pressure. Okay, but with high melting point and high boiling point, they are solid at room temperature and pressure. Okay, why do they have high melting point, high boiling point? Again, a large amount of energy is needed to overcome the strong electrostatic force of attraction between the cations and anions. So large amount of energy is needed, therefore it has high melting point and high boiling point. Okay, the next point that we are going to look at is that the melting points and boiling points of your ionic compounds depend on the strength of the ionic bond. So the strength of the bond, the ionic bond in this case means the ESFOA, the electrostatic force of attraction between the cations and anions. This, how strong is this attraction, is dependent on the charge of the ion. So the higher the ions, higher the charge on the ions, the stronger the ESFOA. Okay, the higher the melting point and boiling point. So what does this mean? Essentially, it means, right, if I have NaCl, which is an ionic compound, and for example, magnesium oxide, which is also an ionic compound. So sodium chloride is made from Na plus Cl minus. Alright, Na plus and Cl minus, while my MgO is made from Mg2 plus and O2 minus. So my magnesium oxide has double the charge. It has higher charge than sodium chloride. The ions of magnesium oxide has higher charge than sodium chloride. Therefore, it has a stronger electrostatic force of attraction. This leads to higher melting point and boiling point. So magnesium oxide will have higher melting point, boiling point than your sodium chloride. Okay, the next property that affects the melting point and boiling point is that the size of the ions. Okay, so the smaller the ionic radius, the closer the cations and anions are, the stronger the ESFOA. Okay, so when your ions are smaller, okay, or you can think of it like a magnet. If your magnet are very close to one another, the attraction is very strong. Immediately they will stick together. But if your magnet is quite far apart from each other, meaning to say it's like a bigger size, in this case, if we relate it to the ionic radius, okay, so if they are far apart, then the attraction becomes weaker. Okay, so weaker attraction will lead to lower melting point and boiling point. Okay, so in other words, the smaller the ionic radius, the stronger the ESFOA, the higher the melting point and boiling point. Okay, so if you remember group 1, okay, the first element is your lithium, followed by the sodium, followed by the potassium. Okay, lithium has the electronic configuration 2-1. Your electrons are arranged 2-1, sodium 2-8-1. Okay, and the potassium is 2-8-8-1. They are all group 1, one outer electron, but the difference is this lithium has 2 shells. Sodium has 3 shells, and then your potassium has 4 shells. Okay, so by this deduction, your lithium chloride, LiCl, will have a smaller ionic radius than the NaCl, than the KCl. Okay, so my lithium chloride will have smaller ionic radius, stronger electrostatic force of attraction, so higher melting point, boiling point. Okay, this one will have the lowest melting point, boiling point. Your potassium chloride will have the lowest melting point, boiling point, because it has the biggest ionic radius, weaker electrostatic force of attraction between the cations and anions. This leads to lower melting point, boiling point.